Namaskar everyone. Today I want to discuss a fascinating real life statistical paradox. Imagine this situation. The City Transportation Authority claims that we release 4 buses per hour. That is one bus every 15 minutes on the average. But when you personally test this system, you find something shocking. Buses seem to arrive not every 15 minutes on average, but at the average interval of much more than 15 minutes. So, who is right? Is the authority lying, or is your data wrong? The surprising answer is both are correct. How? Let us understand how. The Transportation Authority says that the buses arrive according to selection process. This means that bus arrivals are random. On average, 4 buses per hour. So, mean interval between two consecutive arrivals is 15 minutes. Now, suppose you test this claim scientifically. For this, every day you arrive at the bus stop at some random time. Ask people standing there how long they have waited. Then you wait for the next bus. And in this way, you record the total waiting time. After 1 month or so, you calculate. The average waiting time comes out to be much more than 15 minutes. Now confusion begins. Let me explain to you this. Why difference? Why this confusion? Let us imagine 1 hour duration. Suppose bus arrivals happen like this. These are the intervals between buses. 10 minutes, 35 minutes, 10 minutes, and 5 minutes. Now calculate the official average. 10 plus 35 plus 10 plus 5 divided by 4. That is equal to 15 minutes. So the authority is correct. But here is the twist. The crucial question is, when you arrive randomly at the bus stop, are you equally likely to reach in each of the four time intervals? Certainly no. You are much more likely to reach inside a long interval. Why? Because it occupies more time. A 35-minute gap gives you 35 opportunities to reach inside it. A 5-minute gap gives you 5 opportunities. This is known as inspection paradox. It is also called length biased sampling. Statistics quietly biases your experience here. We have in this sample 4 time intervals: 10, 35, 10, and 5 minutes. Taking the discrete approximation, the expected observed waiting time would be, that is, expectation of t, t is the waiting time. So expectation of t is equal to summation t pt, probability of t. This is equal to 10 into 10 by 60, 35 into 35 by 60, 10 into 10 by 60, 5 into 5 by 60. So this becomes 10 square plus 35 square plus 10 square plus 5 square whole divided by 60, which gives the average of 24.16 minutes. It is not 15 minutes. Now, one point here. If we have to find the exact average time, that is without discrete approximation, then we would have to use the density of inter-arrival time as the length biased exponential distribution given by its density f star t equal to t f t by expectation of t, where ft is the exponential distribution given by ft equal to lambda e to the power minus lambda t. Here lambda is clearly 4. In this case, expectation of t is equal to, better to say, expectation star t is equal to expectation of t square by expectation of t. And we know that in exponential distribution, the expectation of t square is 2 by lambda square, and expectation of t is 1 by lambda. So this gives 2 by lambda, and putting the value of lambda 4, it is half hour, that is 30 minutes. Alas, it is double. It is double of the authority average. So we learn from this example that expectation depends on sampling mechanism. This happens because the authority measures departure rate and you measure experienced waiting time. This phenomenon appears in many areas. Waiting time in hospitals, call center delays, traffic congestion, network packed arrivals, even in social life. Now, this paradox teaches us a deep lesson. What we observe depends on how we sample. So, next time you complain, why is the bus always late? Remember, the bus may not be late. Statistics is playing a trick on your perception. And this is the beauty of probability theory. If you enjoyed this explanation of real-life statistical paradox, please like, share, and subscribe to the channel. In our next lecture, we will explore another magical paradox from probability theory. Thank you.